Hello everyone, welcome to eSpace. Welcome to my Loon lecture on sequential circuit analysis and synthesis part 1. In this session we will be talking about sequential circuit. It's a part of digital electronics, introduction, latches and flip-flops, master slave flip-flop, characterization of flip-flop, and flip-flop conversions. I'm Chanjalas Chandran, MTech graduate from IISc Bangalore, working as a senior engineer at Caltron. So about the lecture, it's a theoretical course, BTech level course. As a prerequisite, you should have knowledge on basic mathematics, algebra, Boolean algebra as a part of digital electronics again, and combination circuit. As a part of digital electronics, you should have these two main prerequisites for to study this course, that is Boolean algebra and combination circuit. References I have taken from digital design, Mano, and digital system design by John F Wakerly. So there are two types of digital circuits. One is combination circuit. As I already discussed, you should have a prerequisite knowledge on that. And here in this lecture, we will be talking about sequential circuit. In a combination circuit, the output depends upon present inputs only. But in a sequential circuit, the output depends upon present inputs and present states of storage elements. That's a new element called storage elements. That is, these storage elements are flip-flops and latches, which stores the bits and bytes of the circuit, and the output depends upon these storages. So the output depends upon previous state or otherwise previous inputs of the circuit. So there are two, and there are in the sequential circuit also again there are two types of sequential circuit depend upon the timing of the signal. That is, one is synchronous sequential circuit and asynchronous sequential circuit. In a synchronous sequential circuit, output signal changes at discrete instants of times or due to a constant signal called clock. So in a synchronous circuit, there's a signal called clock, and all the output and input of the system depends upon this clock, and this clock pulses provides a synchronism to the circuit. So just like you can see in the body, just like a heartbeat, the heartbeat gives the timing of the body. So just like that, the clock gives the timing to the circuit. The storage elements used here are called flip-flops, which stores one bit of information. So one flip-flop stores one bit of information. So to store 1 byte of information, there we can group eight flip-flops together to store 1 byte. Like that, we can use any number of flip-flops to store large amount of data. And the second type is asynchronous sequential circuit. Here the output signal changes at any instant of time and the order in which the input signals change. So according to the order in which the input signal changes, the output also changes. So according to the sequence of the signal, the output signal also changes. So here there is no clock, but only here also there are some storage elements. Here it is called latches. Here the latches store the information. Then the storage elements commonly used in sequential circuits are time delay. So actually it is a latches only. It is actually latches which stores the bit information, and that is the propagation delay of logic gates are used here. So in the synchronous sequential circuit, there are two types. A synchronous sequential circuit is also called as a finite state machine, which we will be discussing in the next lecture. And in the synchronous sequential circuit, that is a finite state machine, there are two types of synchronous sequential circuit. That is, one is Moore machine and another one is Mealy machine. In the Moore machine, the output depends only on the present state of the system, that is the flip-flop outputs. The state is given by the flip-flop outputs. A state of the system is given by the flip-flop outputs, and so the output depends only on the present state of the system. And in the Mealy machine, the output depends on the present state as well as the external inputs of the system. So the output changes with irrespective of the clock. The inputs are not synchronous to the clock. So while the input changes, the output also changes. So with the output now does not depends upon the completely depends upon the clock. So latches and flip-flop are the storage elements in the sequential circuits. Each stores a 1 bit of information. As I told you, if you want to store 1 byte of information, we'll be grouping 8 flip-flops, in which each flip-flop stores 1 bit of information. So both stores data according to the control input called clock. So both give response the input according to the clock. Clock is nothing but a pulse waveform and it determines the timing and speed of the system. So you have already seen the clock of a processor, just like AMD Ryzen 5, like that. It is usually given in 2.5 gigahertz to 3 gigahertz, like that. So it determines the timing and speed of. If we have a if we have a clock frequency of very high value, the speed of the system will be more. So here latch and the difference between latches and flip-flops is that latch is a level triggered circuit and the flip-flop is a edge triggered circuit. So and the level triggered and edge triggered can be positive or negative according to the type of the storage element. So these are the clock response in latch and flip-flop. So the clock waveforms is just like this. So if you have a TTL circuit, that's a type of family in the digital circuit, we usually call like that. TTL circuit is a transistor, NPN and PNP transistor circuit, and CMOS is another which use MOSFET circuits. So all that for TTL circuit, this voltage varies from 0 volt to 5 volt, and this goes just like a pulse waveform, continuous pulse waveform in the circuit. So this is a response to positive level response to the clock by the latches. So the latches become transparent when it is, we call just like a transparent. The latches, the output of the latches is enabled, and the clock waveform is high. So at these times the clock is the output is enabled. The output of the latches is enabled. That is shown in black color here. And for the flip-flops, for the positive edge triggered flip-flop, the output triggers when the clock goes from 0 to high value, that is 0 to 5 volt. Suppose 0 to 5 volt in a TTL circuit, when the clock goes from 0 to 5 volt, the output of the flip-flop changes. For an ATS trigger, when the clock goes from 5 volt to 0 volt, the output of the flip-flop changes. That is called just like positive edge triggered and negative edge triggered flip-flops. So let us now see a SR latch, a basic latch which stores 1 bit of information, but there are some disadvantages in the circuit which you will be seeing here. So when this is called just like S is called for set and R is called for reset, and this is the QN. This is the output of the circuit. This is the complement of the output. That is QN complement, just like that. So if we have 0 here and 0 here, this is a NAND gate. When the one of the input is 0, the output is essentially 1. So here we have output 1 and QN is equal to 1 and QN bar is also equal to 1. So this is a forbidden state in NAND gate. So when S equal to 0, R is equal to 0, when whatever value of QN is there, output will be 1 1. So we can see here that this is not complementary. So this state is forbidden state. This state is not allowed in the circuit. So suppose now let us see another condition. When S is equal to 0, and R is equal to 1. So this is a active low input. So When S is equal to 0, here one of the input is 0, the output of the NAND gate will be 1. So this will be Qn will be equal to 1. So this one and this one come here. So 1 1, the output of the NAND gate becomes 0. So this is a allowed state here. So here the Qn equal to 1, that is we have the set condition here, and Qn bar equal to 0. This is complementary and this is a allowed state. So this is a set condition, active low. But why it is called active low means when this is you can understand that this S is equal to 0. When S is equal to 0, this is becoming 1. That's why it is called active low input. So we can see in the another condition. We can see another condition when S is equal to 1 and R is equal to 0. So essentially this will be 1, Qn bar will be 1. Why? Because this is one of the input is 0. So the output of NAND gate will be 1, and this 1 goes here, and when 1 and 1 comes, Qn equal to 0. So this is a reset condition of the NAND gate. So that is why so active low input. So R is equal to 0, this become reset, that is Qn equal to 0. So you can see here, that is Qn equal to 0. Qn that is Qn n plus 1 means the next state of the Qn, that is 0. So this is a reset condition. Now again we have one more condition. We can see that the last condition is when both S and R equal to 1. So suppose we have a present state of the Qn. Suppose if it is 0, Qn equal to 0, and this is 1. So this 0 comes here, and this 1 comes here. So 1 1, the value is 0, and here it is 0 1, so it is equal to 1. So there is no change in the output of the flip-flop, output of the latch. So there is no change. So in this condition, 1 and 1, Qn equal to 0, Qn n plus 1 is equal to 0, and Qn plus 1 bar equal to 1. So there's complementary. So Qn plus 1 is a 1. There is no change. Again we can see one more condition is there. We can check that also. Suppose this is 1, this is 1. Earlier we can taken Qn equal to 0. This time we will take Qn equal to 1. This has 0. So this 1 will come here. 1 1 is 0, and this is 0 here. 0 and 1, 0 and 1, it is 1. So there is no change in the state. So when SR equal to 1, S and R equal to 1, there is no change in the value of the SR latch. Okay. So this is shown here in the table, truth table, that is called the truth table. All the conditions. So when S and R equal to 0, this is a forbidden state. Both Qn bar will be 1, and when set, that is S equal to 0, will be set condition, and when R is equal to 0, it's a reset condition. When both S and R equal to 1, there is no change. So let us now find the functionality of SR latch with cross-coupled NOR gates. Instead of NAND gate, now we are using NOR gates. So in this case, the S and R input become active high input. So let us see the functionality. Okay, so now when S and R equal to 0, when S and R equal to 0, so suppose when Qn equal to 0, Qn bar equal to 1, that's a present state. So this 1 comes here. So suppose if any one of the input of NOR gate is 1, output is 0. So this 0 comes here. So 0, 0, 1. So when S and R equals 0, the output does not change. The state does not change. The state remains in the latch remains in the same state. Now let us see the when Qn is equal to 1. This is when Qn equal to 1. So here again x is equal to 0, r is equal to 0, and Qn equal to 1, Qn bar equal to 0. So this 1 comes here. This 1 comes here. So suppose if any one of the input of NOR gate is 1, output is 0. So this 0 comes here. 0, 0, output is 1. So the state maintains the same. Now the state does not change. Qn plus 1 equal to Qn. So this is the first condition. S is equal to 0, R is equal to 0. No change. So let us now see S equal to 0, R equal to 1. S equal to 0, S equal to 0, R equal to 1. So here input is 1, any one of the input is 1. So this would be definitely 0. So this 0 comes here, and 0, 0 makes 1. And this 1 comes here, so it is 0. Again, it is 0 only. So this is a reset condition. So when S is equal to 0 and R is equal to 1, the condition is 0. Output is 0. So it is a reset condition. So let us now find the third condition. The set condition when S is equal to 1, R is equal to 0. So here any one of the input of an OR gate is 1. So this will be 0. So 0, 0, this 0 comes here. This is 1. And this 1 comes here. So again 0 only. So we understood that when S is equal to 1, R is equal to 0, output is 1, essentially 1. So this is a set condition. This is a set condition shown here. S is equal to 1, R is equal to 0, whatever value of Qn, value state of Qn plus 1 will be 1. So let us now find out 1, 1 when both S and R equal to 1. So suppose this is 1, this is 1. See here, any one of the input of NOR gate is 1, output is 0. Again here any one of the input is 1, output is 0. So this is the forbidden state here. Instead of SR latch with cross coupled NAND gate, here output is 0, 0 state is the forbidden state. In the cross coupled NAND gate it was 1, 1, the forbidden state. Here it is 0, 0. So this is another circuit with that is SR latch with control input. Control input means it will be the clock. So when C is equal to 0, when C is equal to 0, definitely the output of this two NAND gates will be 1. So that is the S is equal to 1, R is equal to 1 condition. So that will be, so it will be no change in the circuit. Qn plus 1 will be equal to Qn. Then the next state will be equal to the present state of the system. So when C is equal to 1, it will be complement of the S and R. So that is when S is equal to 0 and R is equal to 1, it will be reset. And when S is equal to 1 and R is equal to 0, it will be set. And when both will be 1, so here we can see when both S and R equal to 1 and clock will be also 1, the output will be 0. So this both will be 1. So that will be the forbidden state of the SR latch. So here we have a new latch called D latch. It is also called a delay latch. Why it is called delay latch we will be discussing in the coming slides. So here this is just like a SR latch with control input where we have taken R as a complementary of S. So there will be only two conditions where both S and R will be complementary to each other. So when here D is equal to 0, then the input of D latch is 0, this will be 1. So this is just like the condition of SR latch with S is equal to 0 and R is equal to 1, that is a reset condition. So Qn plus 1 will be 0 and Qn plus 1 bar will be 1. So that is shown here. This is a reset condition. Now we will take the set condition, that is when D is equal to 1, this will be 0. This is just like S and R, SR latch with set is equal to 1, S is equal to 1 and R is equal to 0. So that is the set condition, that is Qn equal to 1, Qn plus 1 equal to 1, Qn plus 1 bar equal to 0. So that is a set condition here, that Qn plus 1 will be definitely 1, irrespective of Qn equal to 0 or 1. So that is a set state and reset state. So when C is equal to 0, here it will be, this 2 will be definitely 1. So and this will be no change. Right, 0, 1, 1, 0. Okay. And when C is equal to 1, C is equal to 1, this it will be according to the condition of 0. So when C is equal to 0, there will be no change. So this is a graphic symbol for latches. This is a clock input for SR latch and D latch. It is a clock input. Here is a D and it's a Qn and Qn bar. Both are complement output. Qn and Qn bar are complement to each other. This shown Qn bar is shown by a bubble here. So this is a circuit of JK flip flop. Here and here the forbidden state of SR latch is avoided. Here when J and K is equal to 1, the output is Qn bar. Qn plus 1 is equal to Qn bar, that is the output is complementary of the present input, present output. So you can see here when clock is 0, this is don't care. Whatever the value of J and K is be, the output is the same. There is no change. That is Qn plus 1 equal to Qn. And when clock is equal to 1 and J and K is equal to 0, then again there is no change in the state. But when J is equal to 0 and K is equal to 1, it is a reset state. Output will be 0. And when J is equal to 1 and K is equal to 0, the output will be 1. That is a set state. And again, I told you earlier, when J and K is equal to 1, the output get toggles. But again, there is some problem with this flip flop also. So there are issues in this flip flop also. That is called the race run condition. So you can see here, still the flip flop is level triggered and the output toggles when the propagation delay is less than the time period of the clock. That is, when the propagation delay of the flip flop is less, or latch is less than the time period of the clock, it toggles. That is, suppose the propagation delay is about 5 nanosecond and the time period of the clock is some microseconds, the output get toggles when the input J and K is equal to 1. When J and K is equal to 1, the output of the flip flop toggles repeatedly within the time period when the clock is high. So what is the solution is either it should be master slave type or S trigger type. So we will be seeing in the next slide what is master slave type, and S trigger type we will be studying in the later part of the lecture, that is in the later lectures. That is a asynchronous design, and in that design it will be the perfect type of edge trigger type flip-flop. So this is a circuit of JK flip-flop with asynchronous preset and clear. It is similar to the same circuit shown in the previous slide, but there is a preset and clear input in the internal NAND gate as shown here. So when preset is equal to 0, then the output becomes 1 asynchronously with independent of the clock. Again, when clear is equal to 0, then output becomes Qn becomes 0. This is as shown here. So you can see here, when preset equal to 0, output is 1. When clear is equal to 0, output is 0. But when both are equal to 0, then there will be a forbidden condition. And this is an active low input, and it works when one of the inputs are 0. You can see here, and when both are 1, it depends upon the JK inputs. This is as shown here, because here this clock is 0. So this is independent of the clock, it will be Qn, and when preset and clear equal to 1, it will be working as a same flip-flop. So this is a circuit for master slave D flip-flop. The same model can be applied for JK flip-flop, and this is a solution for race around condition for the JK flip-flop which we had discussed earlier. And this is a negative edge trigger type. Why it is called negative edge trigger type? Because the output of the flip-flop changes when the clock goes from high to low, and it is shown here when the clock is 0 or high, whatever the D input is, independent of the D input, the output does not change. That is the Qn plus 1 equal to Qn. And when here you can see here, when the clock goes from high to low, at that edge, when the D input is 0, the output makes no change. That is a reset mode. And when clock goes from high to low, again then at the negative edge, and when D input is 1, then the output goes to set mode, that is goes to 1. Why it is called master and slave? Because the output of the slave follows the output of the master, which is connected to the D input of the slave. And here you can see here, at the high state of the clock, the output of the master changes according to the clock, according to D input, and when the clock is high. But when the clock goes from high to low, this data, whatever stored in the high state of the clock, that bit at the master output is transferred to the output of the slave output. That's how it works. And as I told earlier, this same circuit can be applied for the JK flip-flop to make a edge triggered JK flip-flop. So this is a D flip-flop operation of a positive edge triggered D flip-flop. So here I will show you why the D, it is called a delay latch or delay flip-flop. Here this is a D input, and this output of the flip-flop will change at the positive edge, that is when it changes from 0 to 1. So at this condition only it will change the output will change. So this is a Q here, it is shown here, that's the output of the flip-flop. So when D is equal to 1 and clock changes from 0 to 1, this will be triggered and Q will be changing from 0 to 1. So again here we see at this time D is equal to 0. So again Q will be 0 at this edge, and again goes like this, and here D is equal to 0, and at this edge it is again 0, and here it goes to 1, and at this edge this 1. So here we can see this waveform, that is this pulse, the negative going pulse will be delayed by 1 clock and coming at the output. So that's why it is called a delay flip-flop. So here you can see this pulse, this negative going pulse is delayed here. That is why it is called delay flip-flop. So now let us see the D flip-flop. let's see the truth table of the D flip-flop. It is same as shown before the master slave flip-flop. The master slave flip-flop has some timing issues because it is we are using the two latches, but here we are using a single JK flip-flop converted to D flip-flop. We can use like that, or we can do any other. There are other circuits for positive edge trigger D flip-flop. So I am not showing the internal diagram here. You can just see the truth table and logic diagram. This is the clock. This shows, it means that this is the edge triggered. In the latch we don't have this symbol, but in a flip-flop we have this symbol which shows it is the positive edge. That is, this is a positive edge triggered. For a negative edge triggered, there will be a bubble here. So this is a positive edge triggered. So when clock goes from 0 to high, and when D is equal to 0, it is a reset condition. And when clock goes from 0 to high, and when D is equal to 1, the Qn plus 1 equal to 1. That is a set state. So that's a reset and set condition, and at all other conditions there will be no change of output. So another flip-flop other than D and JK flip-flop is a T flip-flop. That is, T means it is a toggle flip-flop because there is a toggle condition there, and this can be constructed from a JK flip-flop that can be converted to T, that we'll be discussing in the coming slides. So when T is equal to 0 at the positive edge, Qn plus 1 equal to Qn. So there will be no change in Qn. It is no change in Qn when T is equal to 0, and when T is equal to 1, the Qn plus 1 toggles. That is a Qn. This is an inverted state of Qn. Suppose Qn equal to 0, the output will be 1. If Qn equal to 1, output will be 0. So it is shown the truth table here. We can understand that. And these are the graphic symbols for flip-flops. This JK flip-flop here, and these all are positive edge triggered. Suppose if we want a negative edge trigger, there will be a bubble here. So again, the output here Q bar is there's a bubble here showing it is the inverted form of Q. So these are the symbols of JK, and here just J and K. D flip-flop we have D, and T flip-flop we have T here, and these are the graphic symbol for flip-flops. So now let us see the characteristic equation. That is, a characteristic equation of a flip-flop means that is finding it is a next state as a function of present state and inputs. So next state means Qn plus 1. So Qn plus 1 as a function of Qn and input. Suppose if it is a JK flip-flop, the characteristic equation means Qn plus 1 as a function of Qn and J and K. So we can write a truth table and then find with K map the function of the next state. So first we will see the truth table. This is a truth table. So when J and K equal to 0 and Qn equal to 0, there is no change. So Qn plus 1 will be 0, and when J and K equal to 0, Qn is 1. There is no change again. It is Qn plus 1 1, and when it is 0 1, this is set reset. So we have a reset state here, reset condition here, and when J equal to 1 and K is equal to 0, whatever happens at the Qn plus 1 will be 1, and when J is equal to 1 and K is equal to 1, this is a toggle mode, and Qn plus 1 will be inverted state of Qn. That is, when if Q equal to 0, Qn plus 1 equal to 1, and if Qn equal to 1, Qn plus 1 equal to 0. So we can write, this is the K map, 3 variable K map, Jn, Kn, Qn, and this is the K map. And as I already told earlier, you should have a knowledge about combination circuit and K map, finding the equation with finding the output with K map. So this is the output. This is a Qn plus 1. So we can write here, this is 0 1 0 0 0 1 0 0 and 1 1 1 1 1 0. This is 1 1 1 0. So we can take this bubble, so it will be Jn Qn bar, and here again we can map, we can circle these two variables. So it will be kn bar qn. So we have got here jn qn bar plus kn bar qn. So let us take for D flip-flop. So this is a truth table for D flip-flop. When D is equal to 0, whatever happens at the qn, qn plus 1 will be 0. And when D is equal to 1, whatever happens at the qn, qn plus 1 will be 1. So we can write here, this is a two variable k map. So this is a function for qn plus 1. So can write here 0 0 1 1 1 1. So it is, we can circle this one, we can group this one. So dn qn plus 1 equal to dn. So let us now find the Casey equation for T flip-flop. So this is a truth table for T flip-flop. When T is equal to 0, there will be no change in the output. Qn plus 1 will be Qn. So Qn 0 0 1 1. And when T is equal to 1, it toggles. So when Qn equal to 0, it will be Qn plus 1 will be 1. When Qn equal to 1, it will be, output will be 0. So this we have grouped here. That is 0 1 0 1 1 0 1 0. So there you cannot group any of these things, but you can just see it is a XOR operation between Tn and Qn. So that is Tn bar, this is Tn bar Qn, Tn bar Qn, and Tn Qn bar. So that is a XOR function between Tn and Qn. So let us see now flip-flop conversion techniques. So here the aim is to convert one flip-flop function to another. So we have a given flip-flop and a required flip-flop here. So from the given flip-flop, we are adding a combination circuit which can convert this given flip-flop to a required flip-flop. So we first write given flip-flop input. This is a given flip-flop input as a function of required flip-flop input. So this is a required flip-flop input, and we have a conversion logic. This is nothing but a combination circuit which changes the, which gives the input given flip-flop input to convert from required flip-flop to given flip-flop. So let us now take the example of a JK flip-flop converting into a D flip-flop. So what you have to do is we have to write the flip-flop input, that J and K, as a function of D input. So we have to find a combination circuit logic to get the output at the J and K input of the flip-flop input given that is input given flip-flop input is J and K. We have to find the J and K output as a function of D input. So you write here, this is the input required. So we have to find the D input function. So Dn Qn bar. So when D is equal to 0, Qn equal to 0, the output will be 0 for the D flip-flop. So again here, when Dn equal to 0, Qn equal to 1, Qn plus 1 will be equal to 0. So when Dn equal to 0, Qn plus 1 equal to 0. So here we have to write the function of Ja and Kn. So we will have two combination circuit. That means two output will be there for the combination circuit, that is Jn and Kn with respect to Dn and Qn, from Dn and Qn. So when state changes, so we have to, how we have to write here means, so when state the input of the J and K, when the Qn changes from 0 to 0, what will be the inputs for J and Kn? So one condition is, here it is. So why I'll write here. So when Qn changes from 0 to 0, that is when Qn changes from 0 to 0, it can be either Jn equal to 0, J and Kn equal to 0, or otherwise it can be a reset condition, that is 0 and 1. These are the two conditions for Qn plus 1, 0 to 0. So here we can write it as 0 x. This is the don't care condition, because whatever happens here, it is no value. Whether this is 0 and this is x, the in output of the flip in JK flip flop changes from 0 to 0. So here we have to write 0x. So again now let us see this state, that is when Qn changes from 1 to 0. So 1 to 0. So when state changes from 1 to 0, what will be the flip flop input? First condition, it can be a toggle state, that is it can be 1 1, and another state is, another input is that it can be 0 1. So it can be 0. So it can be, there are two conditions here, either j and k equal to 1, or otherwise it can be j and k equal to jk equal to 0 1. So here we can write it as x1, that is written here, that is x1. So again qn equal to 0 and qn plus 1 equal to 1. So that is 0 to 1. 0 to 1 flip flop input will be, so it can be 1 1, it is a toggle state, and then it can be a set state, that is 1 0. So this we can write it as 1x, that is written here, that is 1x. So again, then when qn changes from 1 to 1, so again we can write it as, can be 0 0, no change in state, and you can give a otherwise it can be a set condition, that is 1 0. So that is x 0, that is written here, that is x 0. I think you have understood the concept. So the same procedure is done for all the other flip-flop conversion too. So let us now to write the truth table. So here it is a Jn as a function of Dn and Qn. This is the output for Jn. This is the input for Jn. So here you can see we have written the same truth table. We have written the values in the K map. So here Jn equal to Dn. Again from this the second truth table, you have written another two variable K map. So here it is Kn equal to Dn bar. So this is the required circuit. So we are giving a complex. This I have shown you earlier in the D latch, converting the JK into D latch. The same procedure is followed here. It is a complement is given by Q1 here, and inverter is kept here to K input. So now let us now try for JK to T. Again there will be a two output combination circuit with the input as Tn and Qn. So again this is the same procedure. Qn 0 to 0 it is 0x, 1 to 1 it is x0, 0 to 1 it is 1x, 1 to 0 it is x1. So here we have written the two table we have written here, and in the K variable and the two variable K map, Jn equal to Tn, Kn equal to Tn. The two functions, two output are there for the common circuit. So this we can short it here so that it becomes a T flip flop. So let us now try one more example. We can convert D to JK. So that is pretty easy. So we have required flip flop into that the input of common circuit are Jn, Kn, Qn, and the output is Dn. So when Jn, and it is Qn, here written as Qn here. When Qn is changed from 0 to 0, the input is Dn input is the input of the Dn is 0 and 1 1. So you can just write the same order as this one. When Qn plus 1 equal to 0, Dn will be 0, and Qn plus 1 equal to 1, Dn equal to 1. So we can just write blindly here this 0 1 0 0 1 1 1 0. This same value comes here at the DN. So that is 0 0 0 1 1 0 0 0 0 1 1 1 1 1 1 0 0. And now let us write in the K map. So Dn will be a function of Jn, Kn and Qn. So that's it. There will be a 3 variable K map. So I have written the values here in the K map accordingly. So this we can group here, that is Jn and Qn bar, and here we can group this one, these two, and it can be Kn bar Qn. So this is the function here, Dn equal to Jn Qn bar plus Kn bar Qn. So this is the required circuit, Jn Qn bar and Kn bar Qn. So this is a combination circuit which has two inputs. These are the Qn inputs are also there, but these are the main inputs, J and K, and is given output to the D flip flop. So this is a conversion of D flip flop into J and K flip flop. So let us see another example of converting D flip flop to T flip flop. So we can write here again, write flip flop input D as a function of T input. So when Qn changes to 0 to 0, output is 0, input that Indian input is 0, Qn 1 to 1 is 1, 0 to 1 1, 1 to 0 0. So we can write in the two variable K map, that is Dn as a function of Tn and Qn, 0 0 here, 1 1 0. So we can group it. So this is Dn equal to, this is Tn bar Qn and this is Tn Qn bar. So that is an XOR function between Tn and Qn. So the circuit becomes like this, Tn XOR Qn. So it will be D. So this is a required circuit for converting D flip flop to T flip flop. So that's it. We can see at the next part 2, we'll be discussing counters and registers and much more. So please like and share the video, subscribe the channel. Thank you. You can, if you have any queries, you can mail me to chanch484@gmail.com. You can add the comments in the comment section. Thank you.